Okay, so we are very happy today to have a professor from Taipe, who is a Peruvian mathematician specializing in quantum symmetries and operator algebraic quantum groupoid. He received his PhD in 2018 from Université de Caen, Normandy, France, under the supervision of Yoni Vennerman and Pierre Fimin. He then held the temporary teaching and research associate position at Université Paris-Saclay, France, working at Laboratoire de Mathématiques d'Orsay. Currently, he holds a research associate position at Instituto de Matemática y Ciencias, Afines, Peru. So today, he will talk about quantum groupoid from quantum group dynamics and Tannaka Krein duality.
Okay, thank you, Sebastian, for the introduction and also for the invitation to talk here. Today, I am going to talk about quantum groupoids, and also, in special, some quantum groupoids arising from dynamics of quantum groups. And if I have some time, I will talk about Tannaka Krein duality at the end. Since my quantum groupoids are not necessarily purely algebraic, I am going to use some operator algebras definition. Then maybe I will try to give some definition in the motivation. Okay, let me start with the motivation for why I'm interested in studying quantum groupoids. And for that, I will give a very brief view of classical Galois theory, since this is the inspiration for quantum symmetries, the original for groups. And well, this is something we already know. Let's see. Okay, if we just start with a field over a characteristic zero field, if you want, well, you have a finite group of automorphisms of this field. You can take the fixed point field. Okay, this necessarily is a subfield of E, and this inclusion is what we call a finite Galois extension. Okay. It does not work because it's sorry, it does not work. Yeah, but the work is not just good. Okay, yeah, it's right. Then this Galois extension has some degree of extension, and this degree is recovered by the order of the group. Okay. Then the Galois theorem says if you have an extension of fields, and this extension is nice, that means finite and Galois. Galois means something normal and separable. This is some algebraic condition. Then there exists necessarily a finite group. And this is what we call the Galois group associated with this field extension, such that the subfield is the fixed point from this group acting on E, and the order of this, or the degree of this extension is keeping in the order of the group. Okay. Furthermore, there exists a one-to-one correspondence between subgroups of G and intermediate fields of this extension. Okay, and this was stated in this way. If you have as a group, you take the fixed point of E, this gives an intermediate subfield, and if you have an intermediate subfield, it's possible to construct a subgroup such that this intermediate field is the fixed point of this subgroup. Then that was very nice as a theorem, but now we want to deal with that for operator algebra point of view. For that, I need some definition. We are going to work with the Hilbert space and with some subalgebra of the bounded operator over this Hilbert space. We say, well, this is a polynomial algebra. This algebra is unital and it's closed using some nice topology coming from the Hilbert space. Okay. In the other sense, if this is closed by a NOR topology, because this bounded operator algebra has many topologies. That means we are going to use now that NOR topology. We call now this a sister algebra. If you see, we have no requiring unital for B in the second point. That means there exists a non-unital sister algebra. Something we already know is every phoneme algebra is a sister algebra. Any finite dimensional sister algebra is also a phoneme algebra. That means for finite dimensional algebras, operator algebras, work with sister algebra is the same as work with phoneme algebras. And some nice link between this topology and algebra is if we consider this commutant, that means giving a set of this bounded operator, you can take the commutant of S, that means all the operator commuting with the elements of S. Then, well, something algebra we can do is S is always in the commutant of S. And there exists a nice theorem that is called the commutant theorem. B is a phoneme algebra, or if and only if B is a star algebra, that means it's closed by the star condition, and is this double commutant is B. Okay, that means this is a very algebraic check if you want to deal with phoneme algebras. Some examples of these operator algebras is, well, you have a compact space, the essential bounded function over X is a phoneme algebra. X is not necessarily finite, that's just means it's not finite dimensional algebras. And from the sister algebra point of view, you can take the continuous function over X with the point-wise multiplication and so on, and you can prove this as sister algebra. Another example is if you take matrix, block of matrix, you make a direct sum. This is a finite dimensional sister algebra, since any block of matrix is a sister algebra. Some nice theorem says any finite dimensional sister algebra is of this form. Okay? That means it's a semi-simple algebra, this finite dimensional sister algebra. Now we need to replace these fields in this context, and for that, let me introduce these two factors. That means factors are phoneme algebras, which are nice. We say a phoneme algebra is a 2-1 factor if it's not necessarily finite dimensional, and they admit a nice functional over M, which is called normalized Feynman trace, satisfy the same property of the classical trace for matrix. And we say it's a type 2-1 if when we look at M in the bounded operator of some inverse space related to M and to the trace, if this admits a representation, a faithful representation in this space, we say this is a 2-1 factor. Okay, this is one way to say. And or type 2. We say it's a factor if the center, which is the commutant, the elements of M concommute with the elements of M. If this is triggered, we say this is a factor. These are nice because they encode some groups, some topological groups. Well, this is convolutional groups. We can construct the phoneme algebra associated to this guy. Okay, it's something similar to the algebra group. But we need to have some topology. That means we are going to make 2 times the commutant of this algebra, and it's possible to construct a trace over this phoneme algebra. And this is a 2-1 factor. Well, some example of that is if you take a free group of 2 elements or 3 elements. This is the phoneme algebra associated to this guy. Gives a 2-1 factor. Another factor who is nice is what we call this hyperfinite 2-1 factor, with some kind of limits of matrix blocks. Okay, we can see the n-size matrix inside 2 times the size in that way. Okay, that means we have some embeddings from M2, M4, and so on. And if we take the union of this is algebra, we can construct a nice trace. And completing this trace, this is the weak topology closure of this. It's not the norm closure. This is some nice factor. Okay. Well, now since we need to deal with degree of extension or degree of inclusion of subfactor, we need what is an index of this inclusion. And already Jones gave this definition before. There was a nice work about him. This was what we call the Jones index. What is basic construction? Given an inclusion of one subfactor, well, as I said before, there is a trace on n, and this trace restricts nicely on n. Okay. And we are going to say this inclusion is reducible if the commutant of n inside some nice bounded operators coming from m intersecting with m, this is trivial. Okay. Well, already people before Jones, they defined some dimension to extend the degree of extension. This is what we call a Murray von Neumann dimension. This is not necessarily an integer. This is the surprise part. This is no integer. And we define the Jones index of this inclusion as this dimension, this analytical dimension of that. Okay. Something we already know is this commutant here. Even if we don't have this condition, this intersection is normally a finite dimensional system algebra. That means it's a sum of block of matrix. The dimension of this algebra is always bounded by this analytical dimension. Well, the surprise theorem of Jones was, well, this index is not necessarily an integer, but in some part it's quantized. That means we are a countable part, and in the other part is continuous. Okay, this was a surprise theorem of Jones. The converse is also true. If you give a number in this set, you can always find a subfactor of this finite one factor who realize the series. Okay, this was nice as a theorem. And starting with this inclusion, we can construct in an iterative way a very big inclusion. This is what we call the Jones basic construction. Something I would just say is, well, if you have this extension, there exists some projections coming from M, and making some construction of polynomial algebra here, you can construct a new polynomial algebra, one containing M. And the nice part is this extension, this Jones index extension is going to be the same of the original index. Okay? Then that means this triple and one is the Jones basic construction, and each two elements discuss the same Jones index. And you can continue using M and 1, and you can construct an M2, another polynomial algebra with one factor, and you can continue many times. And all this tower of polynomial algebras is what we call the Jones tower associated with this inclusion. Okay? This means we have many polynomial algebras over there, all coming from the original inclusion. And since we are not going to work with any inclusion, we are going to work with some nice construction called depth2. What depth2 means, we only need two levels of this inclusion, because in order to understand N and include on M, normally we need all the tower, but for this kind of depth2, we only need these two levels in order to understand the inclusion. Okay. Well, some example of this to a factor inclusion is if you have some inclusion of groups of type ICC, that means who such that is phoneme algebra is to one factor, you have normally this inclusion. LH is included in LG. This is the phoneme algebra associated with each one. And the joint index of this inclusion is nothing else of the index of inclusion of the groups. Another kind of construction of inclusion is if you have one phoneme algebra, you can make act any finite group on M, okay, in a topological way. This is my condition for this topology, for this analytical action. Outer here means this fixed point of the action, the content of this length is trivial. Okay, this is what we already called irreducible before. This is a position only for that.
Can you go through it?
Okay.
It's too much information at the same time.
Okay, yeah, I see.
I guess that that's the kind of situation you want to show us that it mimics Gamma theory.
Sure.
Yeah, okay.
Sure. I mean, I am supposing analytical counterparts for all the construction done by the extension. Okay, here we have an action of G of n. You have the fixed point of this action. Okay, this is a fixed point.
That provides kind of intermediate factor.
No, in this case, because it's it's the objective. And when it's that two, you don't have intermediate factor. Okay, we are going to the more simple one, and then you can study the one who has intermediate factor. It's possible to do that. Okay, that means here we have this inclusion. We have the fixed point included on M with a nice action of G on M. And using joint induction, basic construction, we can construct another phoneme algebra, and this is what we call the cross product. Okay?
First question. The 2-1 factor, is it unique?
No, not necessarily.
They depend on what? What is the moduli of this factor?
That depends. I mean, there is usually someone who are unique. This is what we call amenable to one factor. But if this is not the case, you can have different. Okay, in this case, it's unique because it's amenable.
Okay, so this one is amenable.
Yeah, coming from groups, but amenable. This is. Okay. Okay. This construction for groups we can extend for algebras. Okay. That means we are going to pick finite dimensional of algebras. And if this acts in a nice way on a 2-1 factor, with some analytical condition of this action, again, we can suppose this action is nice in the way to have irreducible inclusion. Again, the fixed point, this time with the fixed point of this action, is going to fix here, and Jones index here is the dimension of algebra. Okay, and these two examples of inclusion are always of depth 2. Okay, it's why I am keeping this depth 2 condition. Okay, that means if you have, well, always finite groups acting to one hyperfinite to one factor, but maybe some natural question is, any inclusion is of this form? This is the Galois question. Okay, because remember for fields, if you have an extension here, always there exists a group. This group acts always in F, and this is the fixed point. Okay, and then this is my question in this framework, giving an inclusion. There exists always a finite group acting on M, such that M is a fixed point. And if we do that on basic construction, is this triple of this form. It means this is a natural extension for this inclusion. Well, the question is no, finite group is not enough to do that. And it was conjectured by Liano that in that case, no, finite groups is not enough. We need to have more. And this more is what we call finite quantum groups. What is a finite quantum group? It's a Hopf algebra. But this Hopf algebra has the property to be a sister algebra. Okay? This is what we call a finite dimensional cat algebra. It's something topological and algebra. And this is the theorem. These three people prove in a different way. Giving an inclusion, well, you need to, in order to construct this Hopf algebra, you need to construct all the tower, all this Jones tower. And in this Jones tower, you are going to compute some relative commutant, these two guys. Okay. And you can endow this finite dimensional sister algebras. I already mentioned these are finite dimensional sister algebra. You can endow this finite dimensional sister algebra with a structure of Hopf algebra. Okay? And those are your finite quantum groups you are going to work with. And also, you can construct an outer action. Outer means you are going to give an irreducible inclusion. Yeah, we are starting with a irreducible inclusion. Having the property we already have for this kind of inclusion. And that means finite groups are not enough to encode this Galois theory in this set. Okay, we need to deal with Hopf algebras here, but no purely Hopf algebras are sister Hopf algebras. One natural question arises now, because in this Galois theorem, we don't suppose this is reducible. Then that means maybe we can drop this condition. The other question is, this finite index condition will relate to the finite dimensional type of quantum object or group-like object we are dealing with. Is necessary to do that? And the question, the answer, sorry, is no. We can do the same kind of construction in these two settings, okay? Dropping this irreducible condition and dropping this finite index condition. And for that, we need to pass to quantum group. It's not enough to deal with groups only. We need to deal with quantum groups. And maybe it's not necessary to break all this. This is for the infinity index.
What do you mean by it's necessary to pass to quantum groups?
I mean,
to get rid of this hypothesis.
Remember, this is some example of an irreducible depth-2. Okay. My question now is the converse. Yeah, if you have an irreducible depth-2 to one factor, this inclusion is of this form as a Galois theorem, and the answer is no. This is not this form. This is mostly of this form using a Hopf algebra.
Okay, so you need to include additional objects to fill the blanks.
Sure. Okay. This is why it's not enough groups. You need to pass to Hopf algebras for do that.
Okay.
Okay. Yeah. This is a particular case of a Hopf algebra. Now, a Hopf algebra coming for a group is, for example, the group algebra. This is an example.
Yeah. Just to be sure, intuitively, a factor, we should think about it as a space of functions or something.
Sure.
Okay.
Yeah. This is why we are using this Hilbert space in which these algebras are acting. Yeah. Okay. This is, for example, this is the theorem for finite index. Here we cannot work with the original Jones work. We need to deal with more analytical type of construction, but it's possible. I mean, you need to suppose some more condition of this kind of inclusion. We are going to keep the irreducible in the depth-2, but we are not supposing the finite index condition. Instead of that, we are going to suppose there exists some kind of map going from M to N. Okay. And if this is possible, well, you can construct a more general Jones tower and same the same kind of construction. This time, those guys are no finite dimensional sister algebra because there are no finite index condition. That means these are sister algebras or fundamental algebras. And that type of object we are dealing with is what we call locally compact quantum groups. Okay, this is something more general of algebras. This is some kind of algebra, but more analytical. Okay, this is why I don't want to enter on this, but we can characterize when this kind of inclusion is a compact type. That means some close to finite condition. In this case, this locally compact quantum group is going to be of compact type, okay, similar to compact groups. If the inclusion is of discrete type, I am not going to enter on the detail of discrete, we can characterize that this kind of locally compact quantum group, this is of discrete type. And if both is compact and discrete at the same time, for the classical case, compact and discrete means finite, yeah. That means, well, this quantum group is going to be finite dimensional. Okay, that means recovering the original of Nyann theory. Then this means now why we're going to pass to quantum groupoids is we are going to drop now this irreducible condition. Okay, remember this irreducible condition means this intersection here was C. Now we are not going to suppose this. That means that could be equal or maybe different. And how this kind of condition detects my kind of group-like object I am dealing with? Well, the answer is, okay, this time, this kind of object we are going to construct is not anymore a Hopf algebra. Hopf algebras are very strong in order to do that. And this strong condition is related to this irreducible condition, okay? And in order to relax this condition, we need to pick this object called weak Hopf algebra. Again, since we are dealing with finite index inclusion, this kind of objects are going to be finite dimensional. Okay, this finite dimensional condition is related to the finite index. And the irreducible condition and inclusion is related to if I'm dealing with Hopf algebras or I'm dealing with weak Hopf algebra. Okay, and what is a weak Hopf algebra? Well, remember, if you have a group, you can construct the algebra group, pick a finite group, okay? This is the Hopf algebra associated to the group. For the weak condition, we need to change the group. We need to relax the condition of the group. And what is the relaxing condition is the finite groupoid condition, okay? That means we cannot start with a group because group gives only Hopf algebras and groupoids give weak Hopf algebras. And what we construct here, well, this is what we call groupoid algebra, okay? And the construction is similar to the group algebra. The only relaxing condition here is the multiplication is not defined everywhere, yeah? Because for groupoids, you cannot compose any elements of the groupoid.
But you can declare the product to be zero.
Yeah, you can do that, but you're keeping some empty information for that. Yeah, yeah, you can do that. You multiply. If you cannot multiply, you say zero, and for the other is the normal multiplication. Okay, this is the condition of relax this compilable condition. And again, you can do the same original construction. You can make this cross product condition, who is nothing else than the next complement algebra construct for the Jones basic construction from this inclusion. Okay, in this case, it's acting on n in a nice way in order to have the nice kind of inclusion. And the relative commutant of this guy are keeping safe here in this algebra here. And this algebra is what we call the target algebra. Okay. Remember, if you're not familiar with groupoids, okay, groupoids are some group-like objects in which we cannot multiply everywhere. Okay, but we can multiply in some nice space. Okay, let me write like this. This is the space of composable pairs of the groupoid. And these composable pairs are nothing else of pairs such that the domain of X is equal to the range of Y, okay? In a categorical point of view of this is I can compose two maps if the range of Y is, if the domain, the range of Y is the domain of X, okay? And these two maps here, which exist relating to the groupoid, this is normally this domain, and this is the range, are going to play some role here. And this target algebra associated with this groupoid keep the information of this inclusion is reducible. Okay? Something we can prove is if this guy is trivial, well, our quantum group is a group. Okay? It's why this is keeping the reducible condition for the inclusion. Okay? Well, this is the theorem. Giving an inclusion which not necessarily reducible, you can construct a finite quantum group, who is called here a weak of Caesar algebra. Okay? Always finite dimensional because we are dealing with finite index. This is a technical condition here only for the categorical equivalence. And all the information of inclusion is keeping in the finite quantum group. Okay? This was done by Mischke and my advisor. And this was why we are interested in studying group. Okay? Because now we want to drop the condition of the finite index. And the answer is yes, you can drop the finite index condition, but this time you need to deal with some we call the short quantum group. Okay, and it's more technical, more to deal with, but it's possible to. And the only problem here is this theorem is announced in a polynomial algebra level. Okay, and this is my versus of these two guys. Maybe I will keep some minutes here and I'll explain. For quantum groups, okay, there existed two ways to study quantum groups in a no-finite dimensional case. One is using sister algebras, and the other is using polynomial algebras. This sister algebra keep the topological information of the quantum group object, and the polynomial algebra keep the measured structure of the quantum group. Okay, but for locally compact quantum groups, there exists a nice theorem of Barre who say if you have a topology in a group, in a locally compact group, you have a measure of this. This is a hard theorem. Yeah? And again, if you have a measure, you can obtain a topology. That means these two languages are equivalent. And for quantum groups, there are people, in this case, it's Kusterman and Weiss, who already prove, yeah, we can do the same. It's not a problem to deal with this topological or measured construction. And another analytical behavior here is we have something we call point-trading dual of that. And this is nice because point-trading duals are an important piece in order to deal with Fourier transform, okay, for groups. Here we also have, that means that applies, we can deal with Fourier transform also for this kind of quantum groups. And the other, and the last and more important, is related with my title, is this Tannaka Krein philosophy. Maybe I will explain here very quickly. Maybe you are familiar with that. This Tanakian philosophy, or for me, who came from typology, is Tannaka Krein. If you have a compact group, okay, well, it's not finite, you can study the representation theory of this, yeah? And if we associate with representation theory, this is a nice category, okay? I am going to represent my group because this is topological I am going to use Hilbert space, not only vectorial space. That means this has a topology inside, and this is what we call a sister category. Okay? It's a category in which the morphism sets of the sets of morphisms has a topological structure coming from some sister algebra condition. Okay? In details, that means the morphism space are Banach space. Okay, and when you take a same object, that means this kind of morphism space, this is a sister algebra always. Okay, that means this is a Banach space always. No, it's not only a set, it's a Banach space this time. But when you pick the same object, this is a sister algebra. This is a special case of Banach space. Okay, that means this is a more rich kind of category. Since this is a group, we can do tensor construction here. That means this is a tensor sister category. And since we have some construction of that conjugate for Hilbert space for, well, Hilbert space R over C, this is what we call rigid tensor category. That means there exists some kind of duals of elements. Okay? And something we have here is if you have two representations, well, you can make the tensor product, and the tensor product is equivalent to this, yeah? This is as a finite groups. That means this is symmetrical also. This is a symmetric sister tensor category. Okay? That means you keep a compact quantum group just to see that this kind of category, and Tannaka can say, if you pick some similar category having this same property, and you add some functor going from C to the Hilbert space, and this kind of functor we call fiber functor. Okay. In this case, what is the fiber functor? Is nothing else of the forgettable functor. Okay, that means we take a representation and we pick the Hilbert space in which the group is represented. Okay, that means we have two pairs of categorical information, and Tannaka can say, having these two guys, you can reconstruct a group here, coming from the category and the fiber font. Okay? And you can, keeping with this group, you can make this construction, and the second statement of Tannaka can say these are the same. Okay? That means you can go from compact groups to this kind of category, and you can come back. Okay? And this is equivalent. That means compact groups, in the categorical point of view, is this kind of nice categorical data. Okay? This is Tannaka Krein reconstruction. The Tannaka philosophy says, yeah, you can this extend for algebraic groups, for example. Yeah, this is a more algebraic geometry. And this kind of statements is also true for compact quantum groups. That means for quantum groups who are compact. That means I can replace this for some quantum stuff. Okay? And what's the difference with groups? This time we are not going to have symmetric tensor categories. Okay? That's meaning this time this kind of property is not enough to have quantum groups. Okay? This is a relaxing property you need to have in order to have quantum stuff in the others. Okay? It's symmetric condition here.
Should it still be braided?
Not necessarily.
No.
Not necessarily. Yeah.
In the,
There exists some case where this is braided, and this is what we call braided quantum. Okay. Okay. This is for the sister algebra. This is for quantum groups. For operator quantum groupoids, we don't have this kind of reconstruction. Okay. This is one of the problem. The other problem is, okay, we have two kind of language we can try to use. The original one is the polymer algebras. The main problem of dealing with that, this use a very technical theory. This is what we call commutative theory. This is very technical. And the bad part of this theory is this not work very well for sister algebras. Okay, there's some lack of condition. The only case we can study very well is the finite dimensional case, because remember, for finite dimensional case, so algebras, sister algebras are the same as polymer algebras. That means we can use algebra technology to study the sister algebra case. But what happens if we want to study compact quantum groupoids? We're not fine. We don't have sister algebra language to do that. Okay? And recently, some people, for example, there was a note, the same note who already proved the Galois theorem for this quantum groupoids, Timmerman and myself, start to use some hope sister bimodules in order to study this kind of sister setting of this quantum group. Okay? The problem is there exists two approaches. Okay? One is model on this kind of host sister bimodules, and another is model on this weak sister algebra. This time is not finite dimension. And what happens here is this framework are not the same. One is inside the other. For example, we have algebras are some kind of host sister bimodule. Okay? That means we have two big language to do that. One is inside the other. For sure, weak algebras is more simple to deal with. And we don't have, so far, the real definition of what is a compact quantum group. Okay? That means we don't have that. And if we don't have the definition of compact quantum group, we don't have this Tannaka Krein. Yeah? Because this Tannaka Krein deals only with compact groups. Okay? And this gap is what was my original motivation to start to deal with kids. Try to study sister algebra quantum groupoids, beginning with the compact groups who are not finite. Okay. That means now we are going to pass to quantum groupoids. And well, before to go for quantum groupoids, for compact quantum groupoids, let me start with compact quantum groups because are the more simple ones. What is a compact quantum group? Well, a compact quantum group is nothing else than a pair. Okay, one is a sister algebra, who is unital, and the other is a map who remembers something close to Hopf algebras. Okay, and sometimes this A we denote as a C of G. And we are going to see why we use this notation. Pick any compact quantum group you like. Take the complex valued continuous function over G. This is normally denoted like this, yeah, C of G. And C of G can endowed with some commultiplication, which is similar to the multiplication for algebras, defined in this way. But the only difference here is the tensor product here. Okay? Because this time these guys are not finite dimensional algebras. This is finite dimensional sister algebra. That's why we need to pay attention of which kind of tensor product we are using here. Okay? And there exists some theorem in operator algebras, which is called the Gelfand duality. What's saying the Gelfand duality? If you take any sister algebra who are unital, this is always of the form C of some compact space. Okay? That means Gelfand duality say you pick a unital, this is a unital sister algebra who is commutative, okay? That means a commutative algebra. In functional analysis, we can compute his specs of this. And this Gelfand theory say, well, this is nothing else of the C of the spec of A. And this is the compact space you are picking with. Okay, that means unital sister algebras who are commutative are nothing else of sister complex valued function over compact space. Okay, but this time we are endowed with a group-like structure. I mean, if we pick this delta here, this delta is going to give some information to the spec, and this information here is the structure of a group. Is why this A is of the form C of a group. Okay, that means this is a way. This kind is all the form, all the compact quantum groups who are commutative are of this form. Okay. Here I am using some technology, use a lot in noncommutative geometry. This is a way we use in noncommutative geometry. We use Gaussian duality, and other examples who are not commutative. Well, the example I already mentioned before, I find the quantum groups. That means finite groups, Hopf algebra, it's a sister algebra structure. But there exists something who are not finite. Okay, and this not finite counterpart, while quantum, is what we call the quantum permutation group, the quantum orthogonal group, and the quantum SU2 group. Okay, this is not finite dimensional, but there are compact quantum groups in this sense. For example, this SU2, it was introduced by Woronovich, and he proved this is a dual way to think about the Dirichlet-Jimbo quantization of the Lie algebra associated to SU2. Okay, that means we have two ways to deal with this kind of matrix quantum group. And as compact groups, there are nice theorems here. One is the hard-type theorem. For compact groups, hard theorem says there exists always a measure. Yeah? A nice measure you can use for all you want. For compact quantum groups, this is the same, but this time it's not a measure. This is not a measure, it's a state. Okay? And what happened in the classical case? Well, for compact groups, this is his measure. You can construct the integral, and this is a state. Okay? This is a state of C of G. I think it's a nice functional in the sister algebra. Okay, this is only for give you a flavor of all the nice theorems for compact groups. It's also possible to have in compact quantum groups. And I already mentioned this Tannaka kind of construction. We can replace this for quantum version. Okay, compact quantum group here now. These kind of categories are not symmetrical. Okay, and why this is important for us in noncommutative geometry is, okay, this is the main technology we can use for construct new examples of compact quantum groups who are not classical ones. Okay. Here I have some part connected with Hopf algebras. These are finite dimensional sister algebras, but always inside this C of G, there exists some nice algebra, and this nice algebra has the structure of Hopf algebra. Okay, that means we can deal with algebraic objects here, and we can come back to this topological using the hard measure, who I already mentioned that exists by a theorem, and using some operator algebra technology called the GNS construction, we can go back to this topological flavor quantum. Okay, this is the connection with Hopf algebras or quantum groups, simple quantum groups. Okay, and this categorical approach is very significant. I already said this allows to construct compact quantum groups, new quantum compact groups. For example, there are some nice class which called partition quantum groups. And this kind of partition quantum groups is playing a very important role in noncommutative probability theory. Okay, this is a way we deal with that. And also for studies on quantum symmetries in noncommutative geometry. Okay, now let me resume this in this. For compact quantum groupoids, what happened? Well, there existed a few theories. There existed a finite quantum groups, I already mentioned before, for the Galois theorem. There exist these compact quantum groups who are a special example of groupoids. There exists another who is called partial compact quantum groups. And there exists another one, again, called compact quantum groups of separable type. I'm not going in details of all of these, but I already mentioned we need to have new examples who are not already pictured here. Okay, and that was the original motivation for me. I want to construct the quantum counterpart of the action groupoids, because action groupoids are a very important groupoid at the beginning. Okay, let me pass this. Well, this is my construction here. Okay, and for this construction, well, maybe let me say very quickly what is an action groupoid. Okay, For an action groupoid, you need to pick a group acting in a space, okay? You can take, for example, finite group acting in a finite space, or a compact space acting in a compact group acting in a compact space. Then it's possible to this cross product here, or this Cartesian product, endow it with a groupoid structure. Okay? This is what we call the action groupoid, or the transformation groupoid. And this groupoid encodes all the information about the action, okay? That means encode G as the first leg, then encode X, and then encode the action, okay? That means in order to see how they encodes, we need to construct all the structural maps of this. For example, the domain is of an element here is the projection over the second one. And the range is the action itself, okay? That means in order to study the action, we can study directly the action group. And this is if you want, finite or compact, but we don't have what is the counterpart of that, okay? Something you can expect is, okay, if we want to quantify this, we need to replace a compact quantum group acting on a space, a compact group acting in space, as a compact quantum group acting in some sister algebra of that. But the answer is no. It's not possible to do that. And they came for a very purely algebraic work done before. And that was new. We already proved it's not possible to do that. We need to deal with more nice action. And this nice action is action of the Dirichlet double of the profile. Okay? I don't want to enter in the details what is a Dirichlet double, but this is equivalent to have another kind of condition, and this is the condition of breaking commutative Dirichlet algebra. Okay? And what is that? Well, a breaking commutative Dirichlet algebra is a triple. That means it's an space, it's a sister algebra, and two actions. One of the compact quantum group, and the other of his dual. Okay? And maybe you are asking why we need two actions. And in the classical case, we don't have these two actions. Well, the answer is, in the classical case, the action is keeping here, and this action here in the classical case, that means when G is a group and N is a C of a compact space, this is a trivial action. Okay? That means in the classical case, this second action, in order to construct a quantum transformation groupoid, is trivial. It's why we don't need this kind of action. But if we need to deal with quantum structure, we need to have another action here. Okay, you need to endow with more structure of this kind of actions.
So by the tool of G,
No. There exists a operator algebraic quantum groupoid dual. Okay, that means if G is finite, this is a Hopf algebra dual. But this is not finite, this is a more topological one, and it's not a Hopf algebra. Okay?
So for like C3 is equal to S3, let's say, then that's the compatible.
Yeah.
Okay.
Yes. Okay, and that means, well, there exists some nice theory, as already mentioned, keeping a compact quantum group. Inside there exists an algebraic core, that means a Hofstadter algebra. That means all this kind of analytical structure will put down in an algebra set. Okay, and this is why I'm giving here. I can construct very purely algebraic things, and let me go directly to my theorem. Okay, I can do the same, but this time I am not going to find a Hopf algebra or a weak Hopf algebra. This time I am going to find something called a Hofstadter algebra. Okay, but it's not a finite dimensional Hopf algebra; it's an infinity dimensional one. And since we are dealing with operator algebra, we need to endow this with more structure, allowing us to operator algebra after. Okay. Some difference, as already mentioned, we cannot deal with weak Hopf algebras. We need to deal with Hopf algebroids. And some nice part And ongoing work here is we can deal with Fourier transform here, okay? And maybe this is okay. This is some nice example I already construct is okay. Maybe I am going to go directly here. If you pick up the factor planar algebra, okay, this is a very combinatorial structure associated to a finite group. Okay, I'm going to start with this very specific case. Well, it's possible to construct an action of a compact quantum group. Okay, no, an action of a finite is an action of a compact quantum group arising from all the combinatorial data of P. Okay, this is a in progress work with Tsinghua. And this kind of action is of the form we need for construct quantum group. That means it's of that type pre-commutative jet action. And there existed some theorem who allows to have this nice structure in order to have a compact quantum group structure here. Some question I am asking now for me, I am wondering, is what is the relation of this compact quantum transformation groupoid with the original planar algebra? Okay, I don't know so far, but this is maybe I'm going to try to attack that. But this is now also for this factor associated to a finite group. We can construct action for any subfactor planar. Okay, we don't know yet if this is of this same form. But this is a connection of subfactor again with compact quantum group. And let me maybe in 5 minutes try to resume all the objects we are seeing before. And okay, this is a big word. This is a wide word of compact quantum groupoids. Okay, let me say here this violet border set. This is a Venn diagram. This is all the world of compact groups. Okay. This yellow border is the world of the compact quantum groups. That means in size and specific case. And this orange border is the finite quantum groups. That means there are some intersections that mean there are regions who are not empty. And there existed these two kind of examples. These green ones, who are compact quantum group of separable times, and this blue border, who are the kind of objects I am working with. And something we already know is these two guys has an intersection, and there exist objects here and objects here. Okay, and we are going to try to find if there exist objects outside this set. And this is an unknown answer so far. And as already mentioned, in order to construct new kind of example, we need to have this Tannaka Krein technology. And so far we don't have. And this is, I am going to finish my talk with that very quickly. Since compact quantum transformation groupoids start with action, we need to categorize actions. And this is already possible. This is any word here. The action of compact quantum groups could be analyzed in a very categorical way. Okay, one way is dealing with functors. This time is no strong tensor functor. This time we need to deal with weak tensor functor. That means that tensoriality is not respected. And another categorical one who is equivalent is modulus system categories over the representation theory. Okay, that means you can study action in this operator algebra way, or you can deal with these two categorical kind of construction. Okay, and this is how we construct this action associated to factor planar algebra. Okay, we use this kind of categorical technology in order to have actions, but we want that.
What does V precisely mean?
Sorry,
Tensor functor.
what is the definition of weak tensor functor? The definition is, okay, we don't have this strong condition. That's me. Remember, for the strong condition, let me put here this more Hilbert finite. Well, the tensor, say this guy is equivalent to this, yeah? This is tensoriality, strong tensoriality. Weak tensoriality says, okay, we only have some map going from this to this, and this guy is only this is only some kind of inclusion, or because we are dealing with.
That is what some people collapse.
Yeah. I mean, we relax this equivalence with the isometry condition. This is the way the tensoriality. And if we have this strong, we can have compact quantum groups. And we have relaxing this way, we have action compact quantum. Okay? And like this, we can find, for example, sub groups in the form of quantum groups. Okay? And for my construction, I need breaking commutative in algebra. That means I need to specialize this kind of with functor or modulus category. And it was already done for other guys, and also for a collaboration with Amori and with Schmidt, who we can characterize when my action has a nice structure along with construct compact quantum transformation groupoids. And for that, we need to put some tensoriality in this module category. Okay, that means this strong condition for being breaking commutative is nothing else as put some tensoriality in the module category. If you see the difference, this is not a tensor category. In this case, it's a tensor category. Okay, that means the tensoriality in this module category encode all these conditions. Okay, and let me say before, let me say quickly, for the classical transformation group, if you do the representation theory, whatever that is, this is encoded in a nice category here, and this category is a module category of the representation theory. Okay, maybe I'm sorry for that. I'm going very fast here, and this is some nice term here. If you pick some module tensor system category over the representation of the compact quantum group and some connected condition, this allows to reconstruct a compact quantum transformation group. This kind of Tannaka-Krein reconstruction is not close to the classical one, okay? Because for the classical one, we need a fiber functor, already arise, but we are close to have. That means this is a partial answer. We need to recover where is the fiber functor, and this is an ongoing work. Okay, try to look at where is the fiber functor. This is kept here normally, and making this, we are at the point to have at least a Tannaka-Krein reconstruction allowing to construct compact quantum transformation group and partial compact quantum groups. And maybe with that, it will be possible to construct new examples to this compact quantum. And let me finish here. Sure.
So for compact quantum groups, there's this canonical hard state.
Sure.
So for compact quantum groupoids, we have a canonical hard system.
Yeah, this is connected to hard system for sure. This hard system, the existing in some specific way of the action. For example, if you look at the classical case, the hard system there exists always if the action is transitive, for example. Okay, if the action is not transitive, you need to put some measure here with quasi-invariant measure, and you have a hard structure over them. In the quantum case, it's the same. You need to put some more information, at least in the base. Okay, this is the case. In the base, you need to put some more structure. But yeah, this is in the hard theorem. We have also a partial answer. Okay, we have some hard structure here, but here we need to put connection. Yeah. Question. Sorry? Of this compact quantum transformation group?
You create some new examples.
Yeah, I mean, I have a machinery to have examples. This is using this question type coideals. This does mean if I have a quantum subgroup, I can construct an action, and this action is have the nice property. And in particular, for planar algebras, I use associated finite groups or finite or for algebras, it's possible to have. This is also an ongoing work. We are constructing some triple doubles of compact quantum transformation groups. And well, if you have a compact quantum transformation group, that means it's of this form normally. We can compute his dual, and his dual also is of this form. Okay, that means is this kind. And that means we can put together and try to look at this. That's really double is also on. But so far, this is an ongoing work. Yeah.
Maybe let me ask, because you were very quick at the end regarding the definition of. So your very general object depend. So it's an action of something on something.
Yeah.
So it's an action of what on what? Just
the necessary object for the construction, yeah. Yeah, I was saying before that for the classical action groupoids are of this form, action of groups on quantum space. We need to replace this for the quantum form. That means we replace this with a compact quantum group. And the quantum version of a space, a compact space, is a sister algebra here. That means we need to replace this with that. But this is not enough. We need to add some other action here. And we don't see this action here because here this action, if you want, is trivial. In this case, it's trivial, but in the quantum case, it's necessary. And all this, so more my condition, this is what we call a jet of field action. Okay, and this is equivalent to have an action for the dream field double of A. It does mean this is what we are going to start, an action for the dream field double of a compact quantum group. And this is the kind of thing we need to construct.
in your big table,
Yeah.
the biggest space.
This is the set of, this is all the compact quantum groupoids. That means we know so far there exists this set. We don't know yet what is outside this two.
And you is the blue.
Yeah, mine is the blue.
And there is no definition for that, you know.
No. I mean, there exists some definition of locally compact quantum groupoid. It's very technical. This was the last work of Enoch. Yeah.
It should be more general than quantum.
Sure. That means you can put some unity condition and you need to pull down all. That means this is why we say there exists this.
It's not a definition.
There exists a definition, but it's very technical. And we don't know if this is the last definition we need to work with. Yeah, because for compact quantum groups, it's only a sister algebra with a map. For this compact quantum group, we want to have the same kind of definition. That means that depends on the example. Yeah. This is why I need to construct more examples.
Any other questions? Okay, so let's think.